Hi, I'm Akshay, and this part is in continuation to our lecture on RLC circuits. Just a quick recap of what was told in the last lecture. So, we have suppose three curves of three kinds of signals: signal 1, signal 2, signal 3. We have three signals. Signal 1 corresponds to this type of waveform, and this is with time. And suppose this is a potential, this is v naught, v naught, this is v naught dash in this, or it's not constant, so let us say this is voltage time curve of signal. So first signal, what we have to do in this exercise is we are given three kinds of curves for three different signals, and we are to identify that which type of curve has either it has an amplitude varying or frequency varying, or it's just that the amplitude is varying but the frequency remains same, or does the frequency is varying but the amplitude remains same. So we have to identify this. I would suggest you to just pause it and solve it for yourself, and then see later whether you've solved it right or wrong. Okay, so pause it for a second. All right, so we know that the amplitude is nothing but the maximum value of the signal in the positive side and on the negative side. So for signal 1, if we see, the maximum value corresponds to this much, and the minimum is, this is minimum value. So we see that all the variations in the values are there, but the maximum and the minimum variation in the values is constant. The maximum on the positive side is only this much variation, and maximum on the negative side is also this much. So we can say that the amplitude of this signal 1 is not varying. So amplitude of signal 1 is not varying. Let's talk about frequency. Frequency we understand by the length of the cuts made on the time axis, the two consecutive cuts. If that length is constant, we'll say that the frequency is constant. So for curve 1, for this part of signal, we see that the length is this much. For this part, consider for this part signal, this part of the signal, length is a little bit more. For this part of the signal, if we see, length is a bit more, and the next part again we'll see that the length has again increased. So if the length is increasing, that means the frequency is decreasing. We cannot say that for sure because this increasing or decreasing pattern is not constant. The increase from this, then it has decreased, then we don't know for scale, we'll have to measure it. So one thing that we can say is that it is not constant, so frequency is varying. So increasing is not a very good word here, so we'll say varying. Okay, so yes, frequency is varying in our signal 1. So similarly, what we can say about signal 2 is that the amplitude is not constant. So amplitude is definitely varying, because on the positive side, this is the maximum for this cycle, this is the positive max, and it is of this side. For next cycle, what we can say is the amplitude is definitely varying. Let's talk about frequency. So we'll just put some points and see the distance. So this much, again this much, almost we can see that it is almost the same length for this part, again for this part. So we can see that the length remains almost constant, so frequency is not varying, it is constant. Similarly, for curve C, it is quite clear that the amplitude is also varying and the frequency is also varying. So depending on the shape, we can identify whether the frequency is varying, whether the amplitude is varying. If the only amplitude varies, we call it a certain type of signal. If only frequency varies, we call it a certain type of signal. And these kinds of variations are usually employed to give and to receive signals and to decode them, to transmit some information in a signal. What we get at our home, AM, that is radio, that is amplitude modulation, in which only the amplitude is changed but not the frequency. Then we have FM, in which frequency is changed but not the amplitude. So depending on the if we understand the context of our behavior of our signals, we can utilize it to do a certain kind of transfer of information. Okay, so now we're going to start our discussion on RL, RC, and all those circuits. So first of all, let's start with RC circuit. The bad part for this lecture is that there is going to be a bit of maths involved, so you'll have to stay with me and understand at every instance. You should understand that what I'm saying is what is voltage and what is the current, so you should understand those terms. So let's draw some RC circuit for a voltage source. Say this is our source, then we have a RC circuit. So suppose there is a resistance and then there is a capacitor, and it's like this. We'll say that the suppose that current flows in this direction I, and we are yet to study for which cycle and everything. Let's just say this is I, and we'll say that the voltage source applied, that is EMF source, the EMF source applied is such that it supplies a potential difference in such a way E is equal to E naught of sine of omega t. So this is E naught sine omega t. What we understand is the frequency of the signal is 2 pi by omega, or omega by 2 pi. The time period of signal is 2 pi by omega. The maximum value of the potential difference that is supplied by the source is E naught. Maximum value is E naught, which is the amplitude of the signal. So we have to find what will be the potential difference across R. What we want to find is potential difference across resistor R and capacitor C, across R and C as function of time. Definitely the sum of the resistor and capacitor at any given time must be E naught sine omega t. Plus there is one more information that we are interested in, and that corresponds to current in the circuit. Current in the circuit. Okay, so let's try to find out how we proceed about it. We know that the combination is in series. The combination is series, so current will remain same. This is series. We can say current in both components is same. So current in both components is same. So we'll say that when we are moving from IR and from say I to R, and then from, say, let us label all these points which we have with us. This is point A, this is point B, this is point C. Now since current is same in this series, and since the applied source of voltage is also alternating source of voltage, the corresponding current that would be induced in the circuit, that would be flowing through the circuit, will also be some kind of changing sinusoidally with time. So we can assume that I in circuit can be written as I naught sine of omega t. Okay, and let us try to find when is the current like this, for what kind of EMF. So suppose our EMF is not sending out E is equal to E naught sine. We have a EMF source which just supplies the current in the circuit, and the current in the circuit varies in such a fashion that I at any time is I naught sine of omega t. So we'll find out what kind of source would produce a current of this kind. Okay, so let us try to write the equation. So potential difference across our resistor would be I naught R sine omega t at any given time. Yes, and potential difference VB minus VC across our capacitor would be Q by C at any time, right? And Q can be directly written as IDT. divided by C. So what we essentially get here is that at t equals to so I naught r sine of omega t divided by C integration from time 0 to t. Or since we are not interested in some limits, we are interested in instantaneous voltage across VB minus VC. So let's try to identify our result in a very generic form. This would give us I naught R by C, there will be a minus sign, and cos of omega t divided by omega. So this will give you I naught R by omega C cos of omega t. We can write this function in terms of our initial sinusoidal form, and if we are writing this function in our sinusoidal form, we can write I naught R divided by omega C sine of omega t minus pi by 2. So we can say this, that okay, so this will be our form, right? For this can be written as, so it is clear that this will be VB minus VC as a function of time, and VA minus VB we know it is I naught R. So if we want to find out, sorry, there is no R in this here. So if we are really interested in finding out VA minus VB plus VB minus VC, that is the EMF of the source provided by the source, so adding these two will get that VA minus VC is nothing but I naught R sine of omega t plus I naught by omega C sine of omega t minus pi by 2. So this will be the net combination, and if we see, it is just like adding two waves of different amplitudes and different phases. So it is we know that this can be solved, that this combination can be written as V would be, which is VA minus VC, can be written as under the root of I naught square R square plus I naught square by omega square C square by omega square C square into cos of sine of omega t into sine of omega t minus theta, whereas we can write that tan theta is such that the tan theta would be 1 by omega RC. Tan theta is 1 by omega RC. So this is our voltage source. So this would be, can be a little more simplified. I naught, we can write this I naught bracket R square plus omega square plus 1 by omega square C square plus 1 by omega square C square to the power 1 by 2 sine of omega t minus theta, where we have tan theta is 1 by omega RC. So the ratio of V by I is called impedance, right? So at any given time, the current, we knew what the current was, sine of omega t. The ratio of V by I is called impedance, and so the impedance Z of the circuit, impedance is denoted by the symbol Z, and the impedance can be directly written as R square plus omega square plus 1 by omega square C square plus 1 by omega square C square to the power 1 by 2. This will be the impedance of the circuit, and let us see that what is this equation, what does these equations mean and everything. So we have a current which is flowing like I is equal to I naught sine of omega t. So at t equal to 0, we have a current of 0, and it increases till 1/4 of its time period. Then it starts to decrease in the second part, then again it still keeps on decreasing in third part, and then it starts to increase and comes to 0. So for impedance, we know we've found the impedance. If we want to find out that if at t equal to 0, if current is in this direction, the ratio, the current vector is in this direction, then and the angle is 0 with this line, with this horizontal line, we can see that the phasor of voltage at t equal to 0, the phasor of voltage at t equal to 0 would be in somewhat different line. It will lag behind. It will lag behind by some value. It's going to lag behind by some value, which is like this. This will be the voltage different across all, and we can see that the potential difference across our capacitor Vc will be lagging behind by pi by 2 with potential difference across resistor. So essentially this value and these two phasors, this part it lags behind by a phase of minus pi by 2, that is minus pi by 2, that means it is lagging behind. So we can write that across our Vc, this is V across R, this is V across C, and at any given time we can see that it lags behind by 1 pi by 2, and these two will give us the summation of these two vectors will give us the V of the circuit. And if this is angle theta, we can say this is phi, since we have already taken theta. We can say that the tan phi would be Vc mod by Vr mod. And what does this tan phi means? It just means that the phasor of resistance, potential difference across resistance, it leads the potential difference supplied by the source by an amount of phi, it leads. So this is it. What other information that we can generate from this circuit is, since voltage across R, the voltage across R, VR and I in circuit, VR and I in circuit are in same phase, that is, the value inside the sine function for I was omega t, and for VA minus VB, that is our resistor, it's also omega t, so they have same phase, while I and potential difference across our capacitor, it is lagging behind. So what is it? We can say that the VC across capacitor lags by pi by 2 with respect to current, in circuit, right? Or we can say with respect to current in circuit, or with respect to VR, because VR and current are in same phase. And again, V across RC combination, that is circuit, V across RC combination, it is also lags behind by tan phi, or by phi, which is equal to tangent inverse of 1 by omega RC. So this will be the complete analysis of this circuit. Similarly, we can do our L circuit as well and our RLC circuit as well. We'll do those questions.